Good afternoon, and welcome to our conversation about high-performance computing and revolutionizing drug discovery. I'm delighted to be joined on the stage by Christoph Gorgulla, who's just flown in from Cambridge. He's a researcher at the Harvard Medical School and also the creator of an amazing platform called VirtualFlow that we'll be talking much more about today. I'm the head of AWS Global Impact Computing. We're an organization inside of the specialist org within AWS that focuses specifically on how to use compute, AI, ML, HPC for social impact, including healthcare, but also sustainability, conservation, human rights, education, and health. We will be speaking today about some record-breaking work that we've done together and implications for even more record-breaking work. So we have a rich set of topics to cover today. We will dive deeply into the cancer and drug discovery related implications of your work, Christoph. And we'll also discuss some recent initiatives to facilitate massive virtual drug discovery screening via what has been, to date, the largest ever known single region HPC run on any cloud. And even though we beat some records together, this is really about the what, not just the how. And so we're going to also talk about the end to these means, which is to identify molecules that block proteins responsible for certainly the hardest to treat cancers, but also other rare diseases and disorders, many of which actually affect populations in economically disadvantaged parts of the world, which obviously from an impact perspective is very important to us. And we'll also get to explore the implications of what we're doing together for precision medicine, and even, and probably maybe even most excited about the democratization not only of the what of this research, but also the who and the how, and how we can use open source platforms like VirtualFlow to increase access. And then we'll end with a little word from our colleague at Intel, Rebecca Weekly. We're delighted to be co-sponsoring, or they actually are sponsoring this session, as well as this initiative with Harvard Medical School. And in fact, AWS and Intel will be working together on a number of 1 million+ core runs in the social impact space. So many more conversations to be had. So a rich agenda indeed. Let's get going. So you, Christoph, and your colleagues at the Harvard Medical School and Dana-Farber have chosen to work on what many call the holy grail of cancer, right? The hardest to treat aspects of this disease. So tell me a little bit about how you got to this work and what motivated you and how you got started down this path.
Yeah, thanks so much for having me. So it started all in my PhD when I did my PhD in mathematics and computational drug discovery. And there I wanted to target a new type of disease targets, which are protein-protein interactions. And they are traditionally very challenging to target because they are very flat interaction interfaces usually between them, and it's very hard to find small molecules which bind tight enough to them. So I wanted to develop a new method for such kind of problems by developing a new virtual screening platform which is able to screen more molecules than ever before. And this platform is called VirtualFlow. And after it was developed several years ago, there was a lot of interest, and so I continued to develop it and then came to Harvard as a postdoc, and yeah.
So you like tough problems.
Absolutely, and particularly in cancer, there are many previously undruggable targets which would be very amenable for this approach.
So this protein to molecule fit that you talk about and that we'll hear a lot more about, it's equivalent to finding a needle in a haystack when the haystack is as big as Mount Everest, right? It's this impossible task of finding this exact fit. And obviously we're trying to productize a therapeutic solution, incredibly problematic. So tell us about the scale of the challenge here. What does this Everest look like in which we're trying to find this needle?
This is a great question. So the chemical space of small drug-like molecules is estimated to contain more than 10 to the power of 60 molecules. That's like maybe roughly as many atoms as we have in our galaxy. So it will be more than we can ever really screen, even with computational methods. But yeah, with the computational approach, we are able to screen much more than with traditional experimental approaches. So we're going now into the billions of compounds already.
So billions of compounds. So we've got this scale problem. And if that wasn't enough, we actually have some what we might call market or industry failure around drug discovery, where this immense task of finding a needle in a mountain the size of Everest, a stack the size of Everest, is actually met with the relative lack of speed and lack of efficiency in the drug discovery business, as it were. So tell us a little bit more about the methodological challenges that you face coupled with these scale challenges.
Right. So yeah, one type of challenge is that it takes roughly 10 to 12 years on average with traditional drug discovery projects, and it costs $2 to $3 billion for a single successful drug in average. And in each year, there are only around 40 new drugs appearing on the market. So we clearly need to improve our methods to develop new drugs. And with traditional methods, like experimental high throughput screens, like they are kind of contributing to these challenges which I just mentioned. They are, for instance, leading to the problem that initial hit compounds are often quite poor in the quality. You can only screen a relatively small amount of molecules, such as maybe 500,000 or a million at the most. And if you do phenotypic kind of screens, then you even don't know how the molecule actually interacts with the target protein. And they're also quite expensive to carry out.
So we've got the scale challenge of the problem, we've got these industry challenges, and it sounds like this is actually compromising the science itself, the quality of the kind of drug discovery that we're doing. So what are you doing about that?
Right. So we are trying to solve this problem by computational approaches, which are able to mitigate all of the issues which I just mentioned. And these are like structure-based virtual screening approaches where we screen large amount of molecules with physics-based docking methods. Yeah, and here you can see also on the slide the principle on how molecular docking actually works. So we have here on the left a protein structure in the surface representation, electrostatic surface, and the cyan-colored molecule is a small molecule which is tested with different conformations on how it could best fit into the pocket. So the docking program estimates like the binding affinity of that small molecule and assigns a binding affinity estimate for each of these tested conformations. So here you can see one with 11 kilocalories per mole, then here one with 12, so it fits a little bit better than the previous one, and now 11.5, a little bit worse. So the docking program for each of the molecules, it tests hundreds of thousands of these conformations to find the best one.
So these are exactly the challenges we're solving together, right? These scale and method challenges. And I think what's interesting about the conversation that we've started is that the computational power that's now available through cloud-based HPC is beginning to inform drug discovery and virtual screening, and this has the capacity to completely change the game for drug discovery, right?
Right, it has a very large potential. It's absolutely right. So one major advantage is that we can screen dramatically more compounds with the computational approaches than with the traditional high throughput screens. This is one major advantage. And this in turn leads to the ability that we can target much more challenging targets as previously, such as the protein-protein interactions. And there are like an estimated 500,000 different protein-protein interactions in the human body, so a new space is opening up for drug discovery.
Great, so tell us more about the hyperscale compute opportunities here.
Right. So yeah, one major advantage, as I mentioned before, is the scale of the screenings. And here you can see a small chemical space, which kind of represents like 100,000 molecules from a traditional high throughput library. And if we compare this now with the billions of molecules which we can screen with computational approaches, here's a size comparison. So like the high throughput, experimental high throughput space with 100,000 compounds, if it's as large as Vermont, then the billion compound space which we are screening now would be almost as large as the surface of the Earth. So it's dramatically much larger.
So the scale and the acceleration that we're talking about in that scale is kind of staggering. I think one of the time perspective that we can talk about here is one of the most exciting things about what we've done, taking things that have normally taken perhaps decades into hours and minutes. So what do you think is possible given our early experiments in terms of reducing the time and also increasing the scale of what's possible in investigation?
Yeah, that's a good question. So when we dock small molecules, it might in average take 15 seconds in average per ligand. And if we would do this, so if we would dock 1 billion compounds sequentially on a single computer with a single core, it would take 475 years. So in universities we have computer clusters, and we might be able to get 5,000 CPUs in average if we are lucky, because there are a lot of researchers who use the same computer cluster. And if we use like 5,000 CPUs, then it might still take several weeks or months even. And yeah, if now with the cloud, we can literally use millions of CPUs at the same time, and then it reduces to a matter of a day or so. So it's a big difference.
That's exciting. And there are also cost effectiveness, right, and other kinds of efficiencies that we can see through this kind of method.
Right. So yeah, one big saving is the time, because yeah, we have time to the type of research as well in the mean, like for the time we saved, and yeah, also if we have better initial hit compounds, like better binding affinities, then we need to optimize the compounds less in the future, like in the optimization phases, and it also leads to efficiencies in the drug development process.
Great. Well, what's exciting about our conversation is that it isn't just theoretical. We, in the last several weeks, have done some very practical work with our colleagues, both at AWS and at your lab, and we've been able to learn from what is the largest ever known single region HPC run on any cloud. We went from your 5,000 CPUs, which I guess you're competing with people at the Harvard Business School doing work on crypto or something. And we've been able to give you access not only to more than 5,000, but almost 2.3 million vCPUs, and doing that over a sustained amount of time, right? Several hours to look at the tens of billions of molecules that we've talked about. So what's so exciting about this for us is that we've been able to, and we'll talk more about this, innovate how we think about the structure and scale and architecture of HPC so that we can respond to the kinds of opportunities that you're seeing in computational drug discovery. And in this case, we were able to do this, as I said, in a single region. We were able to use only excess capacity using EC2 Spot with AWS Batch, and to use only a single family of instances, Intel C5 XL Skylake instances. So I think in microcosm, we're able to begin to prototype a kind of fractal of what might scale very effectively through AWS, and able to support what you're talking about at scale sustainably, and as we begin to talk about VirtualFlow universally, right, across the world to people who normally don't have access to this. I think what's really exciting too, speaking about cost effectiveness, is that we were able to do this, right, in some ways the largest run ever done, given some of these constraints, for $140,000. So talk about radical democratization. I think the efficiencies that we're talking about have vast cost implications, which are very exciting for us to explore together. So what was this like to go on this great experiment with us, to do this run? And we're not done yet. We're going to break more records, but we're kind of halfway through. What was it like to experience this with us?
Yeah, it was a great experience. So we approached you with this kind of project, and we got very positive feedback from you regarding the collaboration. And yeah, together we made this the plan on how we best achieve this goal, and we got a lot of technical support. It was very helpful, and yeah, it was yeah, we worked with several of the scientists from AWS together to scale up to this new record number of CPUs, and yeah, it was a really good experience.
I guess there was a lot of recoding that we had to do, right, to get the platform ready to scale to this level as well. It wasn't just on our infrastructure side. I think we had a mutual set of re-engineering that we had to do, which was very interesting for us as well.
Absolutely. So in order to make VirtualFlow run on this new this new number of CPUs, like millions of CPUs, we needed to rewrite VirtualFlow, some parts of it, And we got a lot of help from AWS on this. And your colleagues really helped to find the best ways to implement this and to make it run efficiently as well. So very grateful for the support.
No, it was a very exciting collaboration, and again, we're not done yet. So now that we've been able to prove that we can do more than we can imagine and drive deeper, faster innovation in drug discovery, we're very excited to think about how science can drive computation as much as computation drives science. And so as we look forward, and we're going to hear more about VirtualFlow itself, what do you think is the potential of this conversation to think about billions of molecules and millions of vCPUs? How does this change the conversation between cloud compute infrastructure and basic research?
Yeah, the cloud computing capabilities, they have a large influence these days on how research is done. And this we can see like with VirtualFlow, which I have developed, because we really try to make use of these new amounts of computational power. And it really changes the way, like also how drug discovery is done. So we are more and more using these virtual and computational approaches in drug discovery. I think it also influences how AWS is influenced by the science. Is it right?
Absolutely, and I think that's what's so exciting about our collaboration. It's very much a conversation, and at Amazon, obviously, we're obsessive about working backwards from customer needs, and in this case, it's the emergence of this scale of possibility, what you can do through an open source platform like VirtualFlow. It provides us an entirely new set of design parameters from which we can think about HPC architecture design, about spot instances, about some of the cost variables that we can begin to drive in different ways. So I think it's provided a really interesting opportunity and challenge for us to think about what hyperscale compute can mean. Certainly this is what's so interesting about the collaboration with Intel as well, is the possibilities of what you're imagining in drug discovery drive our imagination around what we can do on the architecture design front, indeed. So let's hear more about VirtualFlow. I'll give you the controls here because I want you to dive deep. We've done some great work together. We're not done yet on these runs, and I think we watch the space. There's going to be some interesting news coming in the coming months regarding the work that we're doing together. And that in and of itself is incredibly exciting. But I think what's even more exciting is that together we can take VirtualFlow onto AWS and begin to realize the dream that you and your colleague Hari and others have had at Harvard Medical School to democratize both the what and the how and the who around drug discovery. And VirtualFlow is really the core of that. So take us through it. Why did you create it? What does it look like? What does it do?
Yeah, so VirtualFlow is a structure-based virtual screening platform, and it's open source, so available for everybody. And the purpose was really that every researcher in the world can use it for free, can extend it by themselves, adding new features so that it can grow in the directions which like the communities really need. And VirtualFlow was also the first drug discovery platform which is able to carry out these ultra-large virtual screenings in an automated fashion. So now I'm going to give you an overview of what VirtualFlow is actually doing. So suppose you have this beautiful protein for which you want to find new drug candidates. So the first thing which we need is a structure of the protein. And this is traditionally obtained by experimental methods such as cryo-EM, X-ray crystallography, and so on. But since very recently we can also use like predicted structures such as AlphaFold structures. And thanks to AlphaFold and Rosetta Fold, there is basically no structure which we available, like no structure which we cannot target. This is a dream for VirtualFlow and structure-based drug discovery. So the next thing which we need is the ligands, the small molecules, which we want to dock to the target protein. So here in the left upper corner, you can see the chemical space with unprepared ligands, the white dots. And the first module of VirtualFlow, VFLP, VirtualFlow for Ligand Preparation, prepares very large spaces or regions of the chemical space into ready-to-screen format. And here on the right side, you can see the violet stars. They are like the prepared ligands in a ready-to-screen format. Once prepared, such prepared chemical spaces, libraries, they can be used again and again with VirtualFlow for virtual screening, which is the second module of VirtualFlow. And this can be set up in a very flexible way. For instance, we can at first do a very fast physics-based screening with docking programs like Autodock and screen billions of compounds very efficiently. And if we want to increase the accuracy, we could include flexibility of the protein. And here we can include sidechain flexibility or backbone flexibility, because as many of you will know, proteins can be quite flexible as well. And what we would do here, or what we often do, is we take the best few percent of the primary virtual screen and then redock them again with higher accuracy to reduce the computational costs. If we want, we can even do a third stage virtual screening where we could use like free energy simulation-based methods. And they can, for instance, also include quantum mechanical methods, which can be useful if there's like a metal at the active site or at the target site. At any of these stages, we can go to experimental validation, meaning typically we would order a few hundred molecules from the virtual screen, like the best scoring compounds, and test them in the lab. If we want, we can also, like if we have an experimentally confirmed compound which looks promising, but which we want to further optimize, we can also do what is called a virtual analog screen. So here we take our starting compound, search the chemical space for in the entire chemical space for the most similar, let's say 100,000 analogs, and then dock them again with VirtualFlow to get a ranking of the analogs. And then we can test them again in the lab, like the best few hundred or so.
Well, it's incredibly exciting work, and we're excited that it's just the beginning, what you created. Did you create VirtualFlow before you came to Harvard?
Yes, that's right. When I was in Berlin in my PhD, this was one of my primary PhD projects, and I continued it at Harvard.
So it's this incredible privilege to take your personal legacy, not only your academic legacy, and get to build on it. And I think what's so exciting for us is that it has implications for healthcare even more broadly than cancer or even traditional drug discovery. We've had some very interesting conversations with you and your colleagues about how what we're building together could further personalized drug design, precision medicine, and even approaches to things like drug resistance. So talk a little bit more about what we might do together there.
Right. So basically, because there are now the protein structures available for almost every protein, there is almost no disease which we could not try to tackle with these structure-based virtual screening approaches like VirtualFlow. So we can go after many diseases or drug targets which were previously unattempted or unsuccessful, and also rare diseases, for instance, and any other type of disease. So this really democratizes the kind of the disease areas which we can target work on.
Great. And as we've talked about, the democratization is certainly of the kinds of cancers, the kinds of diseases and disorders that we can think about, but it's also about democratizing who is involved in what they're doing. And I think what is so exciting about your vision is that we can think about equity and access of the people actually engaged in this type of research, not only what they're doing, but who's doing it. And certainly from the perspective of our team at AWS Impact Computing, this is central to what we're trying to do, is to bring more equity and access in the global south particularly to what has normally been the remit of very large companies or very prestigious labs like your own. So it's incredible to be able to take this richness, but really make it accessible not only to maybe diseases or cancer types that have been traditionally ignored, but also to researchers who are in places that would never dream, right, of being able to do this. Thanks to your work and what we can do together, we can do that now. So we're excited about matching what you've created in terms of research capacity with compute capacity, and to continue to break barriers there. And I think that diversity and access will continue to augment this conversation between the compute power and the science by bringing in voices that maybe have been excluded and beginning to look at the kinds of issues that maybe have been underrepresented. So it's really a dream for us to be able to think about social impact so specifically and deeply with you. Again, we've only yet started, so we're very excited to continue the work. I'm also very pleased to be able to thank Intel for sponsoring not only this collaboration and others like it that will come with this collaboration around high-performance computing. And I'd like to now play a short video. Unfortunately, Intel was not able to join us here at reInvent. But Rebecca Weekly, who is the Vice President and General Manager for Hyperscale Strategy and Execution at Intel, has a few minutes of a message for us about the kinds of technologies that really underpin the work that we're doing together in terms of Intel instances.
I am Rebecca Weekly, Vice President and GM of the Hyperscale Strategy and Execution team here at Intel. And I'm so excited to talk about Intel and AWS working together. AWS and Intel have a 15-year relationship dedicated to developing, building, and supporting cloud services that are designed to manage cost and complexity, accelerate business outcomes, and scale to meet the future of computing requirements. Intel processors provide the foundation of many cloud computing services on AWS. Amazon EC2 instances powered by Intel Xeon Scalable processors have the largest breadth, global reach, and availability of compute instances across AWS geographies. A few landmark achievements in the last year in the HPC space include Intel becoming an AWS HPC Competency Launch Partner, Intel verifying AWS Parallel Cluster as the first cloud offering certified as an Intel Select solution, and last but not least, Amazon recently launching its first EC2 instance based on the 3rd gen of Intel Xeon Scalable processors. Our latest 3rd gen Intel Xeon Scalable processor launched earlier this year with AWS with the M6i instance. The 3rd gen Xeon processors provide users more performance and flexibility with a generational improvement in performance for customers' HPC workloads specifically. That's thanks to improvement in our core architecture with a 20% jump in instructions per clock, plus increased cache sizes. Xeon is still the only x86 CPU in the data center with built-in AI acceleration. This is the DL Boost 3rd gen Xeon processor with advanced security, including total memory encryption and enhanced cryptography processing. As always, Xeon-based systems are easy to deploy and optimize, both on-prem and in the public cloud, with the development tools that customers are already familiar with. Here is a snapshot of the Intel AWS EC2 instances by workload type that are enabling HPC partners and customers around the world to reach new heights. M6i is utilized for general purpose computing and a broad set of workloads to deliver up to 15% better price performance over previous generations and 20% higher memory bandwidth for HPC workloads. And new to the market for machine learning workloads is Amazon's EC2 DL1 instance, accelerated by the Habana Gaudi AI processors. These are the first dedicated AI training instances from AWS that are not based on GPUs. DL1 is designed for training machine learning models, and it delivers up to 40% better price performance than the current generation of GPU-based instances. With DL1, customers can train models faster and more cost-effectively than ever before. One of the key goals of our joint technology with AWS is to democratize access to compute power through products with strong price performance, in addition to high availability, scalability, and elasticity. When our customers and partners have access to such groundbreaking technology, it enables them to accelerate solutions to the world's most urgent social and environmental challenges. With that in mind, HPC is redefining what is possible and continues to be a strategic workload for both Intel and AWS. And together, we are working on several programs where HPC is not just driving industry advancements, but also positive societal change. HPC has been key to solving the most complex problems in every industry and use case, from weather to health and life science to defense and security. By collaborating with partners and customers, and through enabling them with the latest cutting-edge HPC technology, we have been able to accelerate positive social impact together. From protecting endangered species, such as the Tasmanian devil, to preventing wildfires through simulation processes, to advancing research on genetic diseases. When we break down what this really means for customers, we can take a look at when University of Sydney's Australasian Wildlife Genomics Group migrated their workloads over to AWS, powered by Intel Xeon instances. By doing so, they were able to accelerate analysis time to go from 10 days to 5 hours. This was a huge leap forward in the race against the clock to protect a precious endangered species, such as the Tasmanian devil. Likewise, most recently, with the VirtualFlow open source platform, our technology helped enable cancer researchers to focus on what really matters in drug discovery, instead of devoting time and money and resources towards scaling their compute. We look forward to such outstanding collaborations with AWS, our partner ecosystem, and our customers to help reach Intel's mission, creating cutting-edge technology that enriches the lives of every citizen on Earth, yesterday, today, and for our tomorrow.
Christoph, Intel and AWS are delighted to be powering your work and look forward to continuing to hopefully further the dream of taking VirtualFlow and making it accessible to people around the world. Thank you for joining us. We won't be taking questions from the stage, but Christoph and I will be outside, happy to continue the conversation. Our email addresses are here, more than happy to be in conversation. Thank you for joining us. And we do take your feedback very seriously, so we hope that you will take a minute to complete the survey session. Thank you.